Today we're going to talk about section 9-1, which is identifying quadratic functions. And so among a few things, what we're going to do is we're going to be able to identify what a quadratic function is, we're going to be able to graph what a function is, and then we're going to learn about some characteristics of what a quadratic function is going to have. So there's certain things that a quadratic function possesses that some other functions don't possess, and we're going to talk about those in a little bit of detail. So the first thing that we talk about is we've already kind of seen what a quadratic equation looks like, but we also know from the last chapter that quadratic also means that this is some kind of polynomial that has a degree of 2. And so if we look down here at this graph and we see what appears to be some equation, we can see that this right here, this is a polynomial with a degree 2. And so as we look at this, we have what we call a standard form that all these quadratic equations kind of hold. And that standard form is used in a variation of variables and some constants and basically some input-output. And so basically what we end up with is that our standard form is y equals ax squared plus bx plus c. Now there are some certain conditions that have to be met, and this is where a does not equal 0. Because if a equals 0, this whole thing, this whole term, goes away, and then it wouldn't be a quadratic equation anymore, because then it doesn't have a degree of 2. But b and c can be any number. So b and c can be 0, and it doesn't make a difference if those two terms go away, because if we look at this original, or this what we remember as from our project, that this is our parent function over here, x to the second power, obviously you see if x stays there and then b and c are 0, those two terms go away, these two terms would go away, and then a would be 1, because remember that's a coefficient, so a would be 1. 1 times x to the second power is just x to the second power. So we can see that that's what that is there. And so what we have is we have a quadratic equation, which happens to be, if we look at this, I'm going to draw a line right down the middle of this, we can see that this is exactly symmetrical. And it's symmetrical around this line. And so these two things kind of mirror each other. And then so what we have is we have this unique shape of this graph, what we call a parabola. So you can also think of quadratic equations having a parabola or a U-shaped. And this parabola can either go upwards or it can go downwards. And we're going to look at these things in a little bit more detail a little bit later. Okay, so now we move on to, so now we've seen a graph. We can obviously look at a graph and see if something is quadratic, but can we do the same thing by just looking at a table? So we're given a couple tables. The first one we can kind of see that it's already going to tell us, okay, this is quadratic because our output says y equals x squared, so we should assume this. But there are a couple things that we need to look for, and those things are, first, a constant change in x. So if we look at this first table, what we're going to look for is that we're going to look for, is there a constant change as we go from x value to x value? And if we look at this, this is plus 1 every time. So from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. The second thing is we look for is a first difference in y values. So our first difference in y values would be the following. So as we look for this, we say plus 1. We look for this, this is plus 3. We look to here, this is plus 5. And then we look here, plus 7. Now what we're looking for is for something to not be the same. So we're looking at this, and remember with linear functions, as the x's change consistently, the y changes consistently. Here it does not change consistently. And so that's what we want. So the first set of differences does not change the same way. And so what we look for then is we look for a second set of differences. So as we look at the first difference, okay, well from 1 to 3, what did that change by? Well, that changed by plus 2. from 3 to 5, plus 2. And then from 5 to 7, plus 2. And this right here, this second consistency, that's what shows us that this is quadratic. So after the first set, which would be linear, those aren't the same, so we go to the second set of differences. So the second set, or the second degree, is consistent, so that second degree means that it's quadratic. So let's look at the next example and see if we can see if this is quadratic or not. So the first thing we're going to look for is we're going to look for a change, or a constant change in our x. So we go from here, this is plus 1 again, plus 1 again, plus 1 again. Okay, so that's good. So let's look at our first set of differences. From negative 9 to negative 2 is plus 7. And then we go plus 1. Then we go from here, this is plus 1 again. And then from here, this is plus 7. Now, okay, well the first set of differences is not the same, so we need to look for the second set. And so from here to here, this is minus 6. This is plus 0. And then this is plus 6. So we can obviously see that this is not consistent. These values right here, these are not the same. So we can say that this table, if we were to graph this, would not be quadratic. That second level has to be the same. As we look up here, these were all plus 2, plus 2, plus 2. That second level of differences was consistent, and so that's what makes it quadratic. Okay, so now we're going to talk about really briefly about graphing these quadratic equations. We've kind of graphed problems and we've graphed all these other things. So a couple tips and tricks for as far as graphing these things. The first thing is we need to make a table. And those tables are going to be values. And so when we make a table of values, we can pick any kind of values that we want, but we just need to create a table of values. And so this here, this is our rule. And so we say if we have x, what is our given y? So if I put in 1, let's say negative 1, let's go with negative 2, negative 1, 0, 1, and 2. Usually about 5 of these things. So 1 point A is use about 5 points. And then what we're going to do is we're going to say, okay, when x is negative 2, what is the answer? So we have negative 2 squared plus 2 gives me 6, because negative 2 squared is 4, positive 4, plus 2 more is 6, and then we can go ahead and finish out the rest of this table. And as you can see, what we have is we have these values that kind of look like they're going to be symmetrical, because we have a 6 here on the bottom, and we have a 6 on the top, then it's 3, then it's 3, then it's kind of 2 is that central middle point. And if we graph these, we can graph these as ordered pairs. So the first one is negative 2 comma 6, so I go negative 2 comma 6, which is way up here, negative 1 3, which is here, 0 comma 2, which is here, 1 comma 3, which is here, and then 2 comma 6, which is way up here. And then our second point here is connect with curved line. And keep in mind, what we're trying to do here is that we have this kind of implied line of symmetry, so we want to make these two halves look about the same as much as we can. So I'm going to go ahead and draw a line through this as best as I can to make sure that those are about the same. Okay, and then there's our graph. So we just have a smooth curve or a parabola to connect these dots. And so whenever we think quadratic, we're always thinking smooth curve. So I'll just supplement this and say smooth curve. And that's pretty much it for graphing. And so I'm not going to, kick you around and say, okay, you need to do a bunch of these graphs, but as long as we remember how to plot points, make a table of values, and then do it. We can also do this with our book app, and that will also give us some idea of the graphing and what these things will actually look like. Okay, so now what we're going to do is we're going to go over a couple of these different parts as far as how we can identify a quadratic equation. So I have two different types of quadratic equations. We have one that kind of faces upward, and we kind of have one that looks like it's facing downward. And so what we have is, if we think about this for a second, what we've got is we've got two things. So first of all, these are both quadratics, and so each one of these things is at the very top of this peak on either side. The very top of this peak, we have two things that we call a minimum and we have a maximum. Now if we look at these two graphs, look at the way that this graph looks. Does this graph go anywhere below this point? No. So that's why we call it a minimum. It doesn't go anything below as far as the y value here. And we call this one a maximum because if we look at this one, the lines or the points don't go any higher than this one. So what we can say is, when we have a minimum, our graph points upward, and we have a maximum, it points downward. We also call these 2 points, both of these 2 points, no matter which ones they are, these are both what we call a vertex. And that vertex is either a minimum or it's a maximum. If it's a maximum, those points don't go any higher, and if it's a minimum, they don't go any lower. And then the last part of this is that what you need to understand is that a vertex is actually an ordered pair. So whenever I say what is the vertex, you give me the ordered pair of that's either the minimum or the maximum. And then what we do is, if we have a minimum slash maximum, whichever one this is we take that vertex and we just have the y value. So for instance, in both of these problems, the vertex is exactly the same. So the vertex in both of these problems is 0, 0. And so the minimum for the graph on the left is 0, and then the maximum for the graph on the right is also 0. So whatever that y value is either our minimum or our maximum, where the vertex is the actual point that we use. So now what we want to be able to do is, when we're not given a graph and I ask you the question, does this open upward or does this open downward, you'll be able to tell me. And so one of the first things that we need to be able to do is, one, we need to use our algebra and put an equation into standard form. Now this is the standard form of quadratic, and so the standard form of quadratic again is ax squared plus bx plus c. So we just have to make it look like that. Obviously not all of these terms are going to exist, but we just have to make sure that we put it this way. And then the second thing is that we have this rule that if a is greater than 0, so in other words, if a is positive, the graph is going to point upward. And then, if a is less than 0 or negative, you should assume then that the graph will be downward. So if a, that number in front, the leading coefficient as we would say, if that leading coefficient of a is positive, our graph is going to point upward. And if it's less than 0 or if it's negative, it's going to point downward. And we can kind of think of that as being true, that if something is going up, we would think that it's positive, and then if it's going down, we would think that it's negative. And so what we can do is we can look at these things and we can say to ourselves, okay, are these in standard form? So this first thing, is this in standard form? Well, no. All we have to do, though, is kind of switch these terms around. And so we can write y equals negative 3x squared, because remember I added the opposite, use my commutative property, plus 5x. I find my a, which is negative 3. So a equals negative 3. This graph And so this graph, since this is negative, is downward. And then if we look at our other example, we have to do a little bit more to get this in standard form. Remember, ax squared plus bx plus c. I need to get this on the other side, so I plus 5x squared. So y equals 5x squared plus 2x minus 6. Okay, I have a here, because that's in front of the x squared. A equals 5, so in this case 5 is positive, so this graph is upward. And that's really all that we have to do to decide whether something is pointing upward or downward. Now, we'll talk at some point about how we can actually find the vertex and the minimum and maximum, but right now we're just going to do that graphically. Now the last thing that we're going to talk about is minimum, maximum, domain, and range. So hopefully we have an idea of what minimum and maximum are right now, and then we have domain and range. So the first things that we're going to discuss here is minimum and maximum. And so what we have is, for a minimum, is when we have an upward parabola and we have the smallest possible y. And then our maximum is a downward parabola, and it's our largest possible y. And so what we need to look for is we need to look for the vertex in each instance. So look for the vertex, and that will help us find it. So the vertex in this first problem here is what we would consider 3, negative 1. And then the vertex here would be negative 2, 5. And so we can look at this one, and this one is going to be a minimum because we don't have anything lower than this. And so our minimum in this case is just negative 1 because it's the y value. In this one here, we're going to have a maximum because this is a downward parabola. And so our maximum y value is 5. And so we can just identify these graphically as, okay, this is never going to go below negative 1 in the y direction, and the other one is never going to go higher than 5 in the y direction. And so that kind of brings us to domain and range, and we've kind of already talked about domain and range. And so the domain and range are as follows. And so our domain is the set of all our x values, and the range is the set of all our y values. So what I'm going to do first is I'm going to label these graphs, and this is going to be graph A, and this is going to be graph B. So for graph A, our domain, now this is the nice thing about parabolas, is that our domain for all our parabolas is all real numbers. And so when we talk about B, so for problem B, our domain here again, so domain is all real numbers, because if you think about this, you start at any x, no matter what it is, and these two branches are going to keep going on forever and ever, and it's going to go basically until infinity. And so when we talk about the range, now the range is where our minimum and maximum are going to come into play. So our range, now we think about, okay, for graph A, the minimum is negative 1. So these y values will never go below negative 1. Now it can be negative 1 and kind of really close to negative 1. And so we use our inequality and we say that our y values are all greater than or equal to negative 1. And in this case, our range over here, now our range now with graph B, we have a maximum, and so our y values are less than or equal to 5, because we can't have anything bigger than 5. We can have 5, but we have to have everything less than 5. So this is saying y less than or equal to 5, and the other one for graph A is y is greater than or equal to negative 1, because if we look at this, this is negative 1 over here on the graph, and it's everything greater than that. And if we look at here, this is positive 5 here, and it's everything less than positive 5. So that's how we get minimum, maximum, and domain and range. Now, again, We can do practice problems, so go through your guided practice and you can do those. And after that, we'll discuss this more in class.